just let me know if I'm audible. Okay. So let's start. Today we'll be discussing some problems related to the bounded linear operators and their norms. I hope my screen is visible. Okay. So let's recall. What do we mean by a norm-linear space? A norm-linear space is actually a vector space with a norm. So suppose V is a vector space and we have some function from V to R such that we had three properties of the norm. First one, norm V is positive for every V and norm V is 0 if and only if V is 0. Second one is the scalar multiplication, K times norm V. In that case, the modulus of K will come out. And the third one is the triangles inequality. Okay. Next we have bounded linear operator. So for that we start with the linear transformation. Suppose T is a linear transformation defined on some norms linear space V1 with some norm V1 to space V2 with some norm 2 be a linear transformation. Then we say it is bounded and say it is a bounded linear function or transformation if it is continuous as well. Also, we have a result that if T is a linear transformation, in that case, T is continuous if and only if the supremum norm T x by norm x for every x in D minus 0 is finite. This basically gives us the norm T. So today we'll be looking at some bounded linear operators. How does their norm look like? Let's start with the first question. Question number 1. Let f from Rn to R be linear if on Rn we take the LP norm and on R we take the usual modulus norm. usual norm. Then what is norm F? Basically, we need to see how does this norm F looks like with respect to these LP norm, LP and usual norm. With respect to these norms, we'll just see how this the operator norm will look like in the case when we are working on a finite dimensional space. Basically, our domain is a finite dimensional space and F is a linear transformation. In that case, we will see how does our operator norm of this boundary linear function looks like. These norms. Definition. Now suppose if X is an element in Rn, then we know that its LP norm is summation I from 1 to n modulus xi to the power p to the power 1 by p. And we have F from Rn to R, a linear transformation. So can anyone tell me explicitly how this function will look like? We have a linear transformation from Rn to R. So can we write it in form of some linear combination?
Yeah, in dot product,
Dot product with
some scalar values in from
those
R.
scalar values will basically will be the image of basis elements. No?
Yeah, yeah.
So this implies there exists some alpha 1, alpha 2 to alpha n in R such that for every x, fx is equal to summation I from 1 to n alpha I xi, where x is an element in Rn. We can see that suppose for by ei, let ei be the vector 0 0 1 1 at the ith position. So in that case we can write for every x in Rn, x can be written as summation I from 1 to n xi ei, and this gives us that fx is equal to summation I from 1 to n xi fei, because f is a linear transformation. If I take alpha I to be fei for every I in 1 to n, so in that case we get fx is equal to summation I from 1 to n alpha I xi. So this is how we are able to write this function in some linear combination form. Okay. So now let's start with p greater than 1. We have modulus fx is equal to summation I from 1 to n alpha I xi. This is less than equal to summation I from 1 to n modulus alpha I xi. So can anyone guess what can we use now? We had some inequalities. So basically I want something times the LP norm of x. In that case, what kind of inequality I can use? We have the Hilder's inequality. So by Hilder's, this is less than equal to summation I from 1 to n modulus alpha I to the power p star 1 by p star summation I from 1 to n xi power p 1 by p. Now this is the LP norm of x, and this is p star norm of the vector alpha, which has alpha i's as its ith element, ith component. So this is here 1 by p star plus 1 by p is equal to 1 by Hilbert's inequality. Now this is equal to the p star norm of alpha times p norm of x, where alpha is alpha 1, alpha 2 up to alpha n. So this tells us modulus fx is less than equal to p star norm of alpha times p norm of x for every x, which tells us that the operator norm, because our operator norm is supremum of modulus fx by norm x p x non-zero Rn minus 0. This is less than equal to, from this inequality we know that modulus fx by norm xp is less than equal to the p star norm of alpha. Therefore norm f is less than equal to norm p star. And this is our equation first. Next, if we are able to find some element in this set such that this norm is equal to norm f, in that case we will get the equality. So let's see. Now taking bi equal to signum alpha I times modulus alpha I to the power p star minus 1. So basically I'm taking a vector b. I'm taking a vector b whose ith component is of this form. So let's see what does norm fx by norm fx by norm x looks like for x equal to b. This implies modulus fb is equal to modulus summation I from 1 to n alpha I. So this is basically modulus bi, na? Alpha I times the way f is defined, alpha I times bi. Now this is equal to, if I multiply this by alpha I, that means basically I'm doing alpha I times signum alpha I, which is multiplied by alpha I to the power p star minus 1. Since any number multiplied by its sign gives its modulus, so this is alpha I to the power p star. This is summation I from 1 to n modulus alpha I to the power p star. So since everything is positive, we can write it equal to alpha I to the power p star, which is basically the p star norm of alpha to the power p star. So we have modulus fb is equal to p star to the power p star. And let's look at norm b. B is an element of Rn, so we have the LP norm on B. This is summation I from 1 to n bi, modulus bi. Modulus bi would be modulus L phi to the power p star minus 1 to the power p whole to the power 1 by p. Now since 1 by p plus 1 by p star equals to 1, this implies 1 by p is equal to 1 minus 1 by p star, which is basically p star minus 1 by p star. This tells us that p times p star minus 1 is actually p star itself. So from here, this gives us summation I from 1 to n modulus L phi to the power p star whole to the power 1 by p. Now I want some p star norm of L phi. So I'll take this to be equal to p star and p star by p. So everything is fine now. So this is alpha p star norm to the power p star by p. So from here we get modulus fp by norm p norm of b is equal to norm p star by p star by p, which is alpha p star, taking p star common, 1 minus 1 by p is basically p 1 by p star itself. So this is the p star norm of alpha. So taking this as second, we had marked that as first. By first and second, we get p star norm of alpha is equal to modulus fb by norm b, which is less than equal to supremum mod fx by x p x belonging to Rn minus 0, because clearly b is a non-zero vector in Rn, and this is less than equal, this is basically equal to norm f, and we have proved earlier above in equation 1 that this is less than equal to the p star norm of alpha. So everything gives us norm f is equal to norm alpha p star. This was the case when we had p greater than 1. So can you try yourself the case p equals to 1? There you won't be able to use the Hilbert's inequality. You will have to try it yourself. So can you try it? In next class, we'll discuss that. Okay. Can anyone just at least write on in the chat box? Okay. Okay, then let's move to the next question. So was this question number 1 fine with everyone? If you had any doubt in any of the step, please let me know. Okay, if not, I'll move to the next question. Question number 2. For a fixed x in Rn, show that limit p tending to infinity, the LP norm of x is equal to its infinity norm, sup norm. Solution. So we'll be mainly using the sandwich or the squeeze theorem. For x in Rn, we have infinity norm of x is equal to maximum I from 1 to n modulus xi. Now this is equal to obviously some xk or some k in 1 to n, and for p greater than equal to 1, the LP norm of this x is equal to summation I from 1 to n modulus xi to the power p whole to the power 1 by p. Now all these xi's are less than equal to modulus xk, obviously, because xk is the maximum. So we can write this is equal to modulus xk, just multiplying and dividing by the term modulus xk. This is xk to the power p whole to the power 1 by p. Now this is less than equal to mod xk times summation 1 to n 1 to the power 1 by p, because mod xi to the power p is always less than equal to mod xk to the power p, because basically xk is the largest term. No? So this gives us n to the power 1 by p times mod xk. Also, really mod xk is lesser than equal to summation I from 1 to n mod xi. I can write it like this. Now taking its power 1 by p, this is 1 by p. So by equation first and second, we get mod xk less than equal to the LP norm of x is less than equal to n to the power 1 by p mod xk. So can anyone tell me how I'll be using the squeeze theorem or the sandwich theorem? So what we wanted to prove that p tending to infinity, this LP norm is basically the the infinity or the supremum norm. Now taking p tending to infinity on both the sides, this is constant with respect to p. And where does this tend? This left hand side term, limit p tending to infinity modulus xk is modulus xk itself, because everything is independent of p. What about the right hand side term? Limit p tending to infinity n to the power 1 by p modulus xk is equal to, can anyone tell me what will it be? So this n is constant. We are taking p tending to infinity. And since n is the dimension, n is clearly greater than equal to 1. So p tending to infinity, n to the power 1 by p will basically converge to 1. So this is modulus xk. And hence by squeeze or the sandwich theorem, limit p tending to infinity norm x p is equal to modulus xk. So this one was some easy thing. I hope you all got it. There should not be any doubt. These are very good examples to remember. Right now, you must be feeling that why we are doing it all repeated, all these things are easy. But in future, you'll realize that these terms will be helpful to prove big theorems. The small parts of those big theorems are basically these questions. Hmm. Okay, then. So can
In
anyone tell me? Yes.
is it true for like sequence space as well? Like let's say x belongs to
Uh,
11. Yeah.
Sequences.
We have taken x belongs to finite dimensional
Uh,
Rn, right?
I can't say because for the case of sequences, we are not in the finite dimensional spaces. Na?
Mm-hmm.
Uh, Sequences.
I think we can't.
Because
No, we can't.
here the sum was finite. In
Yeah.
that case, we don't have finite sum. Na? So I don't think we can do that. We have similar result for LP spaces, capital LP spaces, space of integrable functions. Have you seen such functions?
Yeah. Yeah.
For there also, when we have integration on a bounded domain, if this domain is bounded, in that case only we have such equation. For unbounded domains, we can't say. For similarly for sequences, I don't think we can do that. In fact, I'll see. I'll check whether we can do this or not. I can't say right now. Right now, it seems that we can't do.
Okay. Thanks.
Okay, so can anyone tell me what do we mean by function with compact support? Are you all familiar with the term support of a function? Okay, then I'll just recall. Let f be any function support of f is the set of all functions x such that fx is non-zero, and then we take its closure. Such a set is called support of the function f, set where it is non-zero. So when we are saying that a function is continuous and has compact support, suppose if the uh, range is R, in that case, the support should be some closed and bounded interval type term. Okay, then you'll be able to understand next question. Let CCR is equal to all those functions such that f is continuous and has compact support. For f in CCR, we define the norm as the same supremum norm. Now let B be a bounded and continuous function on R. Define a linear transformation TB from this space CCR, the space of all continuous functions with compact support, to CCR as TBF is equal to BF. Now, since B is a bounded function, bounded and continuous function, F is a continuous function with compact support. This function BF will surely be a continuous function because multiplication of two continuous functions is a continuous function, and it will have a compact support because outside that outside the support of F, F is 0 and hence BF will also be 0. So therefore the support of BF will be basically the support of F itself. So this function is well defined for every F in CCR. Show that the operator norm of TB is equal to norm B. So now by norm B, we mean the infinity or the supremum norm. Now B is a function, continuous bounded function, and TB is the linear operator defined on CCR. So basically, when we are defining a linear transformation by just multiplying by a bounded continuous function, in that case, the operator norm of that transformation is basically the norm of the supremum norm of that function. Now, for F belonging to CCR, we have modulus TBF, sorry, infinity norm. Now, TBF is an element in CCR, and in CCR, we have this supremum norm. This is equal to supremum modulus TB, this is B, F at X for every X in R. Now, what is TBF? TBF is B times for every X in R. This is obviously less than equal to the infinity norm, the supremum norm of B times supremum Fx, because obviously modulus Bx is less than equal to the supremum norm. Now this is equal to B infinity times norm for every F in CCR. This tells us that the operator norm of TB is less than equal to sup norm of B. Let's mark this as equation 1. Now, we know that this norm, infinity norm is supremum. So basically, we are taking supremum over some set. So we know that a property for supremum, that for epsilon positive, then for any epsilon positive, I can find some x naught in R such that if I subtract this epsilon from the supremum norm, that means I'm getting a little bit lower than the supremum, I can find some point x naught such that this will be less than equal to modulus Bx naught. I hope you all must be familiar with this this property of the supremum. Similarly, we have for infimum when we add some epsilon. So in that case, we will get something which is lesser than the term after adding epsilon to the infimum. Okay. So now let F belonging to CCR be such that it is equal to 1 at x naught and its value is less than equal to 1. Clearly, we can find any function. Suppose we have x naught here. I can make some function f. All I need is that it should be continuous and it should have compact support. Suppose this is x naught minus 1, x naught plus 1. If I make some function like this, which is basically straight lines and 0 outside, this will satisfy our conditions. So in this case, norm TBF subnorm is equal to supremum x in R fx bx. Now this is obviously greater than equal to modulus bx naught times supremum norm of f, because supremum over bx is obviously greater than equal to value of b at point x naught. This gives us norm TB, which is greater than equal to norm TBF by norm F. This is greater than equal to mod Bx naught, because clearly F is non-zero. Non-zero. F is non-zero. And now this mod Bx naught is greater than equal to, this is greater than equal to B infinity minus supremum norm of B minus epsilon. Now since epsilon positive is arbitrary, we get norm TB greater than equal to B infinity. And this was actually strict. Yeah, this should be strict. This is equation second. By first and second, we have norm TB is equal to infinity of B. So is this proof fine by everyone? If you have any doubt in any of the step, please let me know. Okay, let's move to the next question. Next question, I would like you to try first yourself. So let's understand the setup. Number 4. Let Cc infinity R be the set of all functions f which are in C infinity R. So by C infinity R, we mean that it is infinite times differentiable and all the derivatives are continuous as well, and has compact support. Define an operator P from Cc infinity R to Cc infinity R as Pf is equal to summation I from 1 to K Ai Fi, where this Ai is a function in C infinity R and is bounded. And this Fi is the ith derivative of f. Now, for n in n, for every natural number n and function f in CCR, we define a norm f in infinity as summation I from 0 to n, the sup norm of ith derivative of f. So basically for any natural number n, because so here it should be infinity as well. So we know that the function is infinite times differentiable, and since it has a compact support, obviously rest of the functions will also have compact support, and hence this uniform, the supremum norm will be finite for every I. So I define a norm like this, so that this P from CC infinity R with norm K infinity to CC infinity R with norm 0 infinity is continuous. So firstly, we should always check whether this defines a norm or not. So I would like you to try this yourself right now. Just check whether this is a norm or not. I'll wait for 5 to 6 minutes, check whether this is a norm or not. After that, we'll see how to show that this function P is continuous. Please try, no? See whether this is a norm. Okay, so I'm leaving this up on you. You try and see how to prove that this is a norm. Firstly, check yourself. That defines a norm on the space C infinity R. So next we need to see whether this operator P is continuous or not. Or in fact, now since clearly P is a linear transformation, if I could show that this is a bounded linear operator, we will directly get that it is a continuous function as well. So for bounded linear operator, if I show that norm Pf, so the norm on the range space is 0 infinity is less than equal to some alpha times norm K infinity. If I show this, then I am done clearly, because if this is satisfied for every f in C infinity R, our domain space, then it turns out that the function is a bounded linear operator. And since clearly by the definition, you can see that this is a linear transformation and a bounded linear operator as well, so directly it will be continuous. So let's see if we can get this kind of inequality. So now let's start with the LHS. Here, 0 infinity. So by 0 infinity, we mean in this summation, we have just the first term, 0th derivative. That means just the supremum norm of f. So this is equal to supremum norm of Pf. Now what is Pf? Pf is summation I from 1 to k ai ith derivative of f. So this is basically the supremum of summation I from 1 to k, write it less than equal to modulus ai x ith derivative of f at x for every x in R. Now clearly this is less than equal to, now this is less than equal to the supremum norm of function ai. So this is less than equal to supremum summation I from 1 to k supremum norm of ai times mod fi x. So on the right hand side, we need some k infinity norm. So for that, we need summation I from 0 to k the supremum norm of ith f, the ith derivative of f. So here also we have so I think, yeah, this should be from 0. So here we will get summation from 0 to k x in R. This is less than equal to 8 times supremum summation I from 1 to k ith derivative of f at x in R, where a is maximum of the supremum norm of ai, where I is varying from 0 to k. Now this can be written as less than equal to a summation I from 1 to k the infinity norm, supremum norm of fi, which is basically the K infinity norm of F. So this is what we wanted. Since F belonging to CC infinity R is arbitrary, we get PF plus 0 infinity norm less than equal to some A times K infinity norm of F. Therefore, P is continuous for every F in CC infinity R. So is this fine? All we need to take care of is the definition of the norm and the linear transformation, how it is defined. So the fact that the functions have compact support and they are infinitely differentiable, that means they are smooth function, is helping us to prove that this transformation P should be a bounded linear operator and hence continuous. Is it fine with everyone? Please respond, at least write in the chat box. Okay.
Also, Nidhi, just wanted like
Hmm?
maybe jumping ahead. Is this kind of transformations being used in like test or like distribution theory? I mean,
Yes, yes. It's used in further while solving partial differential equations. Use there. If you're known to Sobolev spaces and all there.
okay.
Okay, so next question is very easy. I don't want to solve it myself. I want you to solve it and let me know and tell me how to solve it. How to just prove it. I'll 5. Let V be the space F in 0, 1. All those continuous functions defined on those intervals 0 to 1 such that F at 0 is equal to F at 1. Show that V is closed in C01 with the sup norm. So just try it yourself. Start with the Cauchy sequence in the set V. See how it will look like. Use the fact that, okay, I can give a hint. You use the fact that C01 is a Banach space. If you remember, it is done in the class lecture. It is done by this Kesavan sir that C01 should be is a closed space, Banach space basically. So in that case, what can we do?
Cauchy sequence converges.
Hmm. It will converge in C01, but we want it to be in V. So the convergence, convergence in C01 is basically the uniform convergence. It will give us pointwise convergence, and with that, we can show that this limit will be an element in V.
I see. Okay.
So let's write it formally. Let Fn be a Cauchy sequence in V. This implies norm Fn minus F m goes to 0 as n comma m tends to infinity. Now since V is a subset of C01 and C01 is a Banach space, the Cauchy sequence Fn in C01 must converge to some f in C01. Now, since convergence in C01 gives pointwise convergence, we all know that uniform convergence, clearly uniform implies pointwise. Pointwise convergence, we have, so what we want this condition. Our function f is in C01, we want this condition as well. We have f at 0 is equal to limit n tending to infinity fn at 0. Now since each fn is an element of V, this is equal to limit n tending to infinity fn at 1, which is f1. Therefore, f belongs to V. Hence, every Cauchy sequence, every convergent sequence in V will be Cauchy and will be converging to an element in V itself. Therefore, this set V is closed in C01. So I hope it is fine with everyone. Okay. So let's move to next question. It is the last question for this session. I think today we completed very fast. Question number 6. Let ak be a function in C infinity R with obviously finite uniform norm polynomial and 0 less than a less than akx for every x in R Now define, let P be a function from Cc infinity R to Cc infinity R, defined as Pf is a function in Cc infinity, which is basically a linear combination of its derivatives. Not linear combination because ai's are not scalars. So we are basically multiplying the ith derivative with the function ai. Show that there exists a constant C positive such that the k infinity norm of P, k infinity norm is as defined above in the previous question. This is less than equal to the 0 infinity norm of Pf. Now since Pf is a function in CC infinity, we have 0 infinity norm defined, well defined on the function pf plus k minus 1 infinity norm on f. This should hold for every f in CC infinity R. So can you just try and tell me how should we proceed?
Uh, the capital A that you have defined, is it a it's a scalar value, right?
It's a constant, positive number.
Okay.
Okay, you can start with the fact that PF is equal to A1F. So this is A naught times F plus A1 times F dash and so on. So from there, we have we can explicitly write the kth derivative of F. Okay, so I'll explain. Solution. We have PF is equal to A naught F plus A1 F dash and so on up to AK kth derivative of F till K. So from here, we know that the functions AI are strictly positive. They are non-zero. The AI is never zero for any point. So I can divide everywhere with the function AK. So from here we get Fk is equal to 1 by AK times Pf minus A naught F plus A1 F dash and so on up to AK minus 1 Fk minus 1. So from here, if I see the supremum norm of Fk, this is less than equal to supremum norm of 1 by AK times Pf. So I'm using just the triangles inequality plus summation I from 0 to K minus 1, the infinity or supremum norm of AI times ith derivative of F. Now see, now the supremum norm of 1 by AK times Pf is equal to supremum modulus 1 by AKX times Pfx for every x in R. Now since for every x in R, AK modulus AKX is greater than A, so 1 upon modulus AKX will be less than 1 by A. So I can take that constant outside. This is less than equal to 1 by A times supremum mod Pfx x in R. And this term is the sup norm of Pf. So this is Pf infinity by A. So using this in above equation, above inequality, we get the sup norm of Fk is less than equal to sup norm of Pf by A plus summation I from 0 to K minus 1 AI Fi. Now this is less than equal to Pf infinity by A plus a constant C summation I from 0 to K minus 1 supremum norm of ith derivative of F, where the C is maximum I from 0 to K minus 1 from AI infinity. So I've just taken the supremum norm of all the AIs and their maximum. Obviously, every term will be less than equal to this maximum term. Now this gives us, so what do we want? We want here the K infinity norm. This implies the K infinity norm of F, which is summation I from 0 to K Fi infinity. Now I can split this sum into summation I from 0 to K minus 1 plus the I equal to K term. For I equals to K, we have this type of inequality. So this is less than equal to small infinity norm of Pf by E plus C times summation I from 0 to k minus 1 Fi plus k rest of the terms. This is less than equal to C bar times uniform norm of Pf plus summation I from 0 to k minus 1 Fi infinity, where this C bar is just the maximum of 1 by A and C plus 1. And see this term. This is the k minus 1 infinity norm of F. This is equal to C bar times infinity norm of Pf plus k minus 1 infinity norm of F. This is what we wanted. This is what we had to prove. Now, since F belonging to CC infinity is arbitrary, we are done. Is this proof fine with everyone? If you have any doubt in any of the steps, please let me know. Okay.
I think in question number 4, we proved like the similar kind of inequality. So it's like sandwiching the PF0, or shall I say a norm of FK infinity, right? It
In fourth question,
Yeah, in fourth question we had like PF0 infinity is less than norm of FK infinity, and here we have proved that it will be less than some one more term, right? PF0 infinity plus,
mhm, plus some extra term.
yeah,
We are getting some k minus 1 infinity term as well. No?
yeah.
We can say that it's sandwiched in between these two terms.
Equivalence of norm or something like that. Is it like that?
Um, because this is k minus 1 infinity, we can take this on the left hand side. But that that constant will anyways give us the equivalence. No? Maybe we can say that. So we have
Yeah. Anyway, I'll give a think on this.
yeah. I think we can do that. All just we need is to formulate a proper proof.
Okay.
I think we can do that. I'll also check. I'll see. I'll tell you in the next class. No?
Thank you.
So, any other doubt?
In the next tutorial, will we be solving the subjective assignments again? Because
Uh, you want to do those practice sheet?
yeah, I mean like Han
Okay,
Banach.
actually, I couldn't get time to solve that practice sheet. I'll try if I could. Then you want to solve the practice sheet for this week, na?
Yeah, right,
Okay. Yes, those Han-Banach theorems, na? It's the application of Han-Banach theorems.
right.
Yes. In next tutor, I'll solve that surely.
Thank you.
Okay then. Okay, if you don't have any doubt, you can leave. Thank you, Hiralal.